lovely people. Welcome to PyLadies Conference 2023. I'm Ivy, your MC for the APEX sections. And for this sessions, we have Pavithra Eswaramoorthy presenting to you. Pavithra is a developer advocate at Consite, where she works to improve the developer experience and community engagement for several open source projects in the PyData community. Currently, she maintains the Pocket Visualization Library and contributes to the NumPy and conda store projects. Pavithra has been involved in the open source community for over 5 years, notable as a maintainer of the Dask library and an administrator for Wikimedia's OSS programs. In her spare time, she enjoys a good book and hot coffee. Now, data science work irrespective of domain is always done in teams. This talk, Pavithra is going to share some tools, principles, and best practices for collaborations while using PyData libraries, with focus on infrastructure like Jupyter and conda tools. We'll discuss some collaborations related to the gaps and potential solutions for the ecosystem. The top title is Collaborations, Infrastructure in Data Science, the Tools, Challenges, and Best Practice. Pavithra, over to you. The stage is yours.
Thank you. That was a wonderful introduction. So I will not repeat that, but just maybe make a note that I go by at Pavithra ES on most places on the internet. And I present as an Indian, light brown-skinned woman with short, curly black hair. I'm wearing a gray shirt today. You can't tell, but it's my PyLadies India shirt. And with that, we can get started with narrowing the focus down. Python is very broad and it's used in so many different areas, but this talk is going to focus on the PyData ecosystem, Python data science ecosystem as suggested by my talk title. And this ecosystem consists of libraries for numerical and scientific computing that often interoperate really well. So on the right is an image created by the authors of Array Programming with Python. You can check that out later. But you can see foundational tools like SciPy, NumPy, matplotlib are probably tools you're familiar with, but there is a wide, broad range of technique-specific, domain-specific, application-specific tooling in this ecosystem, which is why Python has become one of the leading languages for data science, right? And in data science across domains, especially you can see there's astronomy, economics, chemistry. In all of these domains, data science almost always happens collaboratively. It's not one person doing things. It happens in teams. It can be big or small, right? I'm using this term very openly. It can be 2 people, or it can be 20 to 200 people. It can be a formal collaboration in a research group, or informal for a hobby project. So more often than not, you're likely working in teams. And I really like this image from the Turing Way project. The Turing Way, if you don't know, it's a community-led handbook for open research, but generally reproducible and collaborative data science. And there are a few different aspects to think about to make things collaborative and reproducible. So we need to share our data, code, tools, and results. I just figured this is a very nice figure to get started with, but we'll narrow down and more concretely describe these, right? So things we need to collaborate are sharing our code and applications code, Jupyter Notebooks, scripts, and applications like visualization dashboards or anything else. Specific tools include their own dashboards, which we also want to be sharing with folks. Second important component is your environments. By environments, I mean the set of libraries we use to do the analysis, right? Set of libraries and packages like NumPy and SciPy. You're using a set of tools. We want to make sure the same set of tools and the right versions are shared with your collaborators. And third is compute resources, which becomes apparent in larger groups, because especially, for instance, you need GPUs or you need a cluster because a cluster of machines because you have a large amount of data. Your collaborator also needs these resources to be able to work with you together on this project. So these are the key components, and these fall under the umbrella of infrastructure tooling. So these are what we need, but there are a few more things this infrastructure needs to have, right? So how we need this to work. First off, we need this to be flexible and fairly easy to use because it needs to compete with individual workflows that people are a lot more familiar and accustomed to. Next is we want to maintain high standards because in any form of infrastructure, where more people are working together, a lot of data is being shared, we need to be very mindful about the security and governance practices that go into this infrastructure. And third is we need some form of management. Again, as we have several people working together, we want to be able to manage and hand out resources. So things like GPUs are expensive resources. So we want to make sure only folks who need it get that, right? So these are the things we need. Now, good news, we have open source tools for these. And if, especially in the Python and PyData ecosystem, if you're already part of these communities, JupyterHub would have come to mind first. For folks who probably don't know, JupyterHub is a platform, or it's a way to, it's a platform, right? It's a way to provide computational resources and share environments with groups of users. And JupyterHub is awesome. It's a community-driven project by the Jupyter community, folks who also create Jupyter Notebook and Jupyter Lab. And it's container-friendly. It can be deployed across any cloud or HPC clusters. And we have options, projects that help you deploy JupyterHub. So Zero to JupyterHub and Litless JupyterHub are projects that help you do that. And one of the best parts, in my opinion, about JupyterHub is it's extremely flexible and very, very extensible, right? Like you can integrate it with many tools within the PyData ecosystem and beyond, actually. So, and talking of tools that we integrate JupyterHub with to make it even more powerful, an important one to note is scale. We talked about clusters of machines before when we discussed compute. And this again becomes apparent in larger teams. So by large, I mean it can be when you're working with even 5 people, that's like fairly large compared to depending on what kind of work you do. But honestly, at this point, like a lot of folks are moving towards larger data sets and scaling and distributing. It's become part of a lot of workflows. So Dask is a very cool library that helps you do this. It is, again, a PyData NumPy sponsored project, which means it integrates well with the existing tooling that exists. And Dask can scale to several clouds and HPC clusters as well, similar to JupyterHub. And there are, again, several projects within the Dask umbrella that allow you to do these well. This is not the only option, though. We have Ray, Spark, probably something else that you can use for scalability. But I'm just highlighting this as something we need to think about in the initial infrastructure building stages. This should not be like an afterthought, which needs a lot more thinking. So we need to integrate Dask in your platform or like any other scaling tools from the beginning. Second thing we need to do pretty much across the board is authentication and access, right? And an open source option is Keycloak. If you haven't heard about Keycloak, it provides a single sign-on options and user management features. So it comes with a dashboard, like an admin console that you can use to add people, manage access, make sure they have certain resources. That's part of our managing compute and user story. And alternatives are Auth0, which might be more familiar to folks. But Keycloak is a cloud-native incubated project, I think. That's why I'm highlighting that here. But these are just 2 key things. There are a lot more you may need depending on your particular use case, right? But for your particular data science work. Next is the main challenge in this story is we still need a little bit of DevOps experience to set these together. So the three main things I just discussed, which is the platform, scaling, and authentication, these three crucial, in my opinion, parts are also actually not as straightforward to make work together. So that is a challenge I think there are folks working on it. And one potential option for us, like I work at OneSite, and something we did I want to share, not in like a let's see this tool kind of way, but like these are some things we incorporated for our particular use case. So let's start with the use case before we actually go to the tool itself. So we needed to, our particular use case is we want to be able to easily spin up and maybe tear down platforms, because OneSite is a consulting company. We work on different projects, right? Different client projects all the time. So the deployment story needed to be a little easier because it's not always folks with DevOps experience deploying things. We have folks who are just data scientists, and they also need to be able to spin up a platform to work with a few more people. So we created this in the form of a tool called Nibari, but I'm going to highlight just a few things we did, which you may also want to consider doing. So for the deployment story itself, we ended up creating a CLI wizard that generates a YAML file, and the YAML file is used as the source of truth for both deploying the JupyterHub system, but also managing things. So you can have a set of instance types. So like by default, everyone gets 2 GB CPU, 2 core CPU and so much RAM, right? So you can set those things and manage and change that later, like in the YAML file, and redeploy, things will change on the platform. So this was a much faster and quicker way to handle the main challenge that I mentioned earlier. And a couple more extra things is integrating some tools by default. So things like Argo and VS Code we saw were being used so often that we integrated in the platform itself. So this is a very opinionated option, right? And thirdly is we created an extension or plugin mechanism. So any tool that needs to be incorporated at the infrastructure level can be incorporated in a slightly easier way. It still needs some knowledge of how things work behind the scenes, but it just makes it a little easier. So with that, I will again reiterate, things change depending on your use case. Maybe you don't need any fancy infrastructure. The basic core JupyterHub works for you, which is fine. And I really like 2I2C's overview of services. I'll totally encourage you to go check this out for yourself. I won't go into the details, but there are a lot of options in this space, especially when you think of like commercial options. And everyone has their own, small niches within this space. So, okay. And you might have noticed I conveniently skipped over environments because this is its own big challenge, especially data science environments. Python packaging, I'm sure everyone has their own, a lot of opinions, a lot of frustrations with it. But when it comes to data science environments and packaging in this space, we have some extra things to consider, which is there are a lot of different languages and packaging options. So different languages, most data science libraries are not pure Python packages, which brings a unique set of challenges, both for the core packaging folks, but also end users. Second is, if you haven't noticed, data science moves really fast. So things are moving and changing really fast, and things may not all libraries are always going to be backwards compatible. So our tooling needs to account for that. And lastly, our workflows also tend to break environments, and we'll get into this in the next slide. There are a lot of options in packaging. I am going to focus on conda, which is used a lot in the PyData ecosystem. But a few of these can be generalized. I do want to say we can narrow down further into conda now. And I wanted to share some best practices around conda, just as this slide can be used honestly separately from the rest of the talk, because this in itself is going to make the reproducibility story much better. These are very basic things. First off is using an environment specification like an environment.yaml or a requirement.txt without, just generally, right? Just providing this in itself is a first step. Next is creating log files. In Conda, we have a tool called conda log that you can use to generate a log file. A log file is basically the exact library version, but like it points to the correct, exactly the file that was used. Like I think it's the tarball, but I might be wrong there. Apologies for not verifying that earlier. But creating a log file is just a full snapshot of the things you used and all of the dependencies. So this makes your work like it's a snapshot. So like if someone is using the log file to create their environment later, it might be you, 5 months from now. You can still have some guarantees around reproducibility. And lastly, this is just a very Conda specific thing where when you add new packages, modifying the existing environment with like install this new package while I'm already activated and in an environment is not the best way to do things. It will be like modify the environment spec and recreate the environment. This does not need to happen for every single package, but doing it often enough and incorporating it into your workflow will go a long way towards, having a little bit of a stabler environment. Okay, next is again so Conda is an internal tool we developed to manage these challenges and best practices. And a few things I want to highlight around like the principles behind these tools, so maybe more folks can follow, is categorizing environments by namespace. This was a very collaboration first tool. Like Conda was a collaboration first created for collaboration. So namespaces is not a Conda thing. It's a separate concept only existing here. But the only thing it does is like creates, oh yeah, you can see my pointer. So it creates certain categories and I can create and edit environments within these spaces. So when I share an environment within the analyst namespace, everyone else in the analyst space can access it and immediately use it. A few more things are we built for reproducibility. So the logs and artifacts section here shows you the log file, YAML, and a few other artifacts are built by default. I don't have to do this manually, but every time I create an environment or edit it, these are built in the background, which is great for reproducibility because anyone else building this environment is going to be using those files. We introduced version control, which honestly, love version control. I'm sure folks will agree. And adding this to environments this in itself is super, super helpful. And lastly, a bonus was the user interface that you're seeing here. This enabled a lot more people, non-developers as well, to participate in following these good environment management practices. So with that, I will just conclude this talk. The key takeaways was this talk was just trying to shine a spotlight on the collaborative nature of data science and the tooling we have. There are some challenges and a few ways to overcome them, but as was evident, folks are thinking about it and things are improving. A quick acknowledgement slide for my colleagues at OneSite who worked on these tools, and with that, I will say thank you and open for any questions if we have time.
Thank you, everybody. Bye.